2. Hi, stream! Welcome back to another great day of EXAG.
EXAG Day 2! So hopefully you enjoyed the industry case studies this morning. That was a lot of fun.
Yeah.
We're going to have 2 paper presentations now, and then we are going to let you out for lunch at noon. You have a nice 2-hour lunch break today, instead of 1.5 hours yesterday. And then we're going to follow up with demo presentations in the afternoon.
Yeah, so without further ado, we have our first, as I scroll up to the top to set this up right, speaker.
Thank you. I'll just stand in this view here.
Right there
and okay. Good morning, everyone. We're all still a little bit sleepy. My name is Adam Smith. I'm going to be telling you about a game that I've made with 2 students that I brought with me. Where are they? In the back there, Nick and Mason. And we're all from the new Design and Reasoning Lab at UC Santa Cruz in our new Department of Computational Media. So to start, I wanted to give you a little taste of the game before I go into talking what it is. So here's a simple game that I think would be wildly unreasonable to make if you didn't have access to a certain AI technology. It happens to be something called ASP. Without saying what this is, who has heard of answer set programming? Okay, well that's a lot. Probably because you went to this event last year and you've heard from me over the years. It's not just me using it now. So if I can get the mouse over to, which direction is that screen?
It is this way. Where's the mouse?
Oh, it's already over here. Cool. So if you want to follow along at home, hold on, let me get a new tab, Control T. We're all going to proofdoku.com, and okay, seems like it loaded right. I'm going to start. I'm going to say, give me the New York Times medium difficulty puzzle for today, and we'll start. Many of you have seen Sudoku gameplay before, so we're trying to fill in cells here based on clues and these other numbers in terms of what numbers have been used in each row, column, and cage. The big difference in Proofdoku is that you don't just like click on a cell and immediately type in what you think it is. Sorry for the light blue on light blue here. I actually have to read the screen a little bit to guess what number should go in here. Anybody in the audience can guess what goes in here? It's not a 5, it's not a 6. 8's, well, we could be like, well, I don't know, let's ask. What's that? Okay. And well, some of the reasoning would be like, there's a 3 here, and there's a 3 here. There's a 3 here, and there's a 5 blocking that one. Computer's pretty convinced that that's the unique value must be there. So I've convinced it. It's like, I'll put in a 3 for you. And you can imagine we repeat this process until we filled in the whole board. But every time we clicked in here, some AI system has either checked our reasoning, has offered us hints, or focused our attention on certain things. Yeah, I'll try. When I'm not giving the demo, I won't be talking opposite you. I just need to navigate the mouse back to this thing.
Right up there.
Cool. Okay, so you saw a tiny bit of gameplay there. For some context, I want to read you this quote out of a paper called AI-based game design, enabling new playable experiences. I'm going to let the authors, some of whom are here, speak for themselves. They said, or at least in 2011, they said, "We argue that to make real progress in innovation for game AI and new forms of gameplay, the AI needs to play a more central role in game development. This paper presents AI-based game design as a practice that makes inroads into the vast space of potential games through the co-formation of new AI technology and games that are heavily dependent on the AI system. By operating in this design space rather than relying on smoke and mirrors, we have the opportunity to take steps towards creating real magic." With sort of a magic metaphor going on. To pull out one thing from there, this idea of co-formation. Suppose you have some game design in your head, you think it's going to feature AI relatively heavily, you start building your AI system, there's context from your game that's pushing back and making extra demands on your AI system, saying, well, can it support this thing? What else can it do? Your AI system may have certain affordances or may have certain capabilities that you haven't yet used in your game, and you might think, well, maybe I could expose those in my game somewhere. So it's not that you build one of these just using the other one as a black box, but you let the design process for these things inform each other in a sort of cyclic flow. There's several games that you could put into this framework just to pick a nice 2x2 matrix. The ones on the left are ones made in an academic setting, Prom Week and Sarah and Sally. Ones on the right are the more commercial setting, The Sims and Third Eye Crime. The ones on the top here, Prom Week and The Sims, are all about social AI systems and simulations of characters' intents and their actions and how those affect each other. The ones on the bottom row, in order to make progress in these games, you're always thinking through what is the AI system going to do in controlling the other characters, often in a planning-like system where you can say, well, because I know it's following a process I understand, I can anticipate its moves and react accordingly to perhaps escape enemies or even cooperate with an NPC in the case of Sarah and Sally. I said I'm building on this technology called answer set programming. You don't really need to know or read code for it or even know too much what it is. The sort of Wikipedia level description of it is answer set programming is a declarative programming paradigm. This is where you write what you want, not how to get it, oriented towards solving complex combinatorial search and optimization problems. You'll see how those show up in Proofdoku in a moment. On the surface, when you're using ASP, it looks like Prolog. On the back end, it runs much more like a SAT or SMT solver. And if you've been following the last few years at many of our AI and games related venues, AIIDE, SIG, FTG, and so on, you might have seen papers on using it for machine playtesting, puzzle generation, progression generation, rule set mechanic generation, even generating little narratives, and even recently interpreting games automatically using logic. But today it's all about how do we use it to make the core mechanics of our game, sort of broadening the horizons of what you do with this. At a high level, in particular, we're using an answer set solving tool called Klingo. I won't say what is happening in the inside other than it is a thing that transforms programs into solutions. And you can imagine that these are logic programming files. They look like Prolog. Over here is some sort of JSON result that we want to interpret in the context of our game. In particular, our game is providing these problem instances, different search and optimization problems that need to be solved quickly in order to respond to the player. Digging into the game design a bit, what I showed you in the live demo, and I can now sort of point at a more slower pace. When we're in the thick of gameplay, can I point to these things? Well, I'll point here. There's one conclusion cell. This is the cell that's currently empty. This is the one we're trying to make an argument for. We would say a successful argument is a proof here. We can have certainly invalid arguments, or we can have wastefully elaborate arguments that offer too much evidence. The evidence, you saw me click on these things, turning them from the light blue to black. You can imagine making a board that has just the evidence cells. So usually Sudoku boards start with 20 or 40 things filled in. Imagine a board that has just those 4 things there. A whole lot of these cells elsewhere here are very ambiguous. There are many consistent values they could take on. But if this is a solid set of evidence, for this conclusion cell, there's only one possible value that could go there. You might have done it through your own modes of reasoning. We're just going to use the rules of Sudoku to say what values are consistent with it. So you don't need to explain the steps of your proof, just sort of the inputs to it. And in order to give you a sense of how the system is thinking, we've done a little bit of shading of all the other cells based on how ambiguous they are. So cells that we know nothing about, like this thing is not influenced by all the other ones. It's at its sort of lightest blue. These things over here that are much more constrained by the evidence I've given get darker and darker and darker, with the limit case being, I think, black, except for the case where it's the conclusion that is flashing saying, okay, I'm convinced that you have an argument. I can click this to lock it in, and it will fill in a, I guess this is going to be a 1 here, because 1s can't go in these rows and columns. Simple arguments might only involve 4 points of evidence. More complicated ones might involve 13 and a whole lot more complicated reasoning. One thing as a player that you can do is you could simply check every box here and say, make a board with all of the clues. Certainly that's enough evidence. It's not the most elegant proof, it's not the most general argument. So we have a notion of optimality, like counting the number of evidence cells, and our game sort of focuses on those with the fewest bits of evidence, the ones that apply to the most other boards out there. So when you're playing our game, you show up at our site, we have a few puzzles available. You first enter the strategy phase where you're deciding what do you want to prove next, and you're not locked into it. You can say, well, I gave up on proving that, I'm going to pick a different goal. So you can go back to the strategy phase if you want. But once you've picked a conclusion cell, you're then in the tactics phase where you spend a while adding and removing evidence, looking at the visualization of ambiguity. Finally, when you've convinced the computer, it says, oh, you want to go back to strategy, I'll fill in that number for you. And eventually you're done, you go to the victory stage. Pretty simple transition between these different states. Throughout the process, there's hints available. I'll say a little bit more on how these are provided later. But in the strategy phase, of all the things you could decide to prove next, like if you just wildly pick on one here, we can ask our AI system, what is the smallest amount of evidence you have to provide to argue that? And it might be something ridiculous, like 23 points of evidence, so like a very complicated argument where the particular constellation of all these things at once nails down the value of this one. But in order to sort of guide your explanation, guide your strategic process, we're going to highlight the cells that are tied for being the ones arguable with the least amount of evidence. Oftentimes, these will be more typical number of evidence cells is like 4 to 8 rather than 22 and so on. But let's say, suppose you click one of those, you're now in the tactics phase. For example, this one as a conclusion down here. But there's lots of things we could select as evidence, and that can be overwhelming. So we provide a hint system that can focus your attention. And the way we do this is because we have access to this oracle implemented in ASP that can reason across all arguments, optimal or not, or maybe enumerate all possible arguments and look at what evidence was used in them. We can say, well, assuming you want to go for an optimal argument, I'll highlight all evidence that is used in any of those optimal arguments. It might exactly be an argument on its own. It might actually be a union of several differently structured arguments, but it means it's safe to ignore the things that are not in there. None of those are needed in an optimal argument. And the moment you start using one of these things as evidence, when you get subsequent hints, it's reasoning about arguments that extend your current evidence set. So it's responding to what you've told us about your reasoning process so far. You think it's very relevant that there's a 7 and a 9 here. Maybe when you ask for hints next, we'll highlight an even smaller subset of those, knowing that it looks like you're trying to make an argument that involves these things, and that might narrow down some of the ambiguity. But there is a lot of complex reasoning here. There's not just finding one argument, finding optimal arguments, finding all optimal arguments, and collecting all their evidence together. Some of our design goals for this system, when I write things like sustainable and evergreen, you might think this is like one of these eco-friendly buildings and so on. Sustainable in the sense that we're not aiming for the game to have a big splash on a certain week and then be forgotten about 2 weeks later. We'd like to make something solid and steady that doesn't cost us almost anything at all, that we can leave running and people can come back to it either day after day, week after week, or find it 2 years later without us having to have poked at it and poured $100 on it a month. Likewise, evergreen here in the sense of sometimes people talk about if you use a modern browser, say Chrome, people sometimes call it an evergreen browser. You're always running the latest version because it keeps itself up to date. You don't need to think when was a new update released, you're just always using the latest one. So we offer not hundreds of thousands of puzzles, but a small set of relevant ones that we happen to, currently we have 1 scraped from USA Today, 3 from New York Times, and currently a few fixed puzzles so that if you are sort of practicing your skills, there's at least 1 familiar puzzle you can go back to at the different difficulties. And these goals shape some of the architecture choices we made later. That's my transition. Before I launch into something about ASP, you might say, well, okay, I'm going to build an AI-based game design that heavily depends on deep learning. But when you go to deploy this, maybe it like works great on your laptop. You're thinking, how do we get this in front of people? Maybe they want to play it on their phones, and of course you can play Proofdoku on your phone. You might have this question of, well, does the player send their data to some server where this big expensive model is, and then data is sent back? Well, now every time someone does some interaction in your game, there's some network round-trip latency associated with that. You might think, oh, we can totally get rid of the latency by sending the model to the client. If they're willing to wait for a very large download up front, maybe this is not something you want in your first few minutes experience where people don't even know what they're interacting with yet, but yet their phone has downloaded 500 megabytes of data. Likewise, depending on where that model came from, you may not want to give that out. That may be your secret sauce. Or maybe the players don't want their data going to some server. Maybe they want to be able to play offline. Depending on your design goals, your expectations about the devices and interests of your players, one of these architectures might be the right thing. Some third or fifth option that I haven't talked about would be the right thing. Over in the world of answer set programming, we don't have models and data. We have programs and solvers. So in the paper, we looked at a few different ways of deploying the system. We made prototypes of these, and I'll tell you eventually, the one we decided on in the end. But it's not because this is like the optimal architecture. It's the one that fit with our goals. So perhaps the simplest way, like if you were